So in this section, we're going to study John Dalton's model of the atom. So this model of the atom was really the first modern model of the atom, and it was put together by an English school teacher by the name of John Dalton in the 19th century, so in the 1800s. And it's a pretty good model. Now, John Dalton was an interesting guy. He had scientific interests in all manner of things, chemistry, meteorology, and he also did a systematic study of color blindness because he was affected by color blindness himself. And so, just by the way, sometimes color blindness, for this reason, is referred to as Daltonism. And so that's kind of interesting. So just to recap, in modern chemistry, we take an atomistic view of matter. We consider that matter is composed of little building blocks called atoms. And these building blocks are indivisible by either physical or chemical methods. And what happens in chemical processes is we combine these different atom types in different ratios and in different, linkages, kind of like putting together the different building blocks that you might have if you've got like a big old bucket of Legos building blocks. So that's really what's going on, right? You can't break any of these atoms apart into small fractions of an atom. You can't change one kind of atom into another kind of atom, but what you can do is join and connect these atoms together in a whole variety of different ways. So that's a kind of a good conceptual idea. John Dalton, as I said, this was in the 1800s, he took things one step further and he developed the first modern atomic theory. Now, you're going to see this kind of described in a variety of different ways, and normally it's not in the language that he used himself, because the language he was using we would consider kind of old-fashioned if we saw it now. But these points kind of really get to the heart of what he was getting at. So the first thing that he said was all matter is composed of tiny indivisible particles called atoms. So all he's really saying here is that all of the other models of matter that don't involve atoms, stop worrying about that. There's no evidence to indicate that those models are any good. The only model that makes any sense is the atomic model. The next point's kind of an interesting one. He said the atoms of one type are all exactly the same as each other. So every carbon atom is the same as every other carbon atom, every hydrogen atom is the same as every other hydrogen atom, etc., etc. But then he goes one step further. He says, and each type of atom is different from all of the other types of atoms. So a hydrogen atom is different from every other atom that we know of. Every other type of atom is different from carbon atoms, it's different from nitrogen atoms, it's different from oxygen atoms, right? Okay, that's an interesting idea. So he's really just saying that these atoms are different types of building blocks and you can't substitute one for the other, that all of the different types of atoms are unique. His third point was to say that it is the number and arrangement of atom types in a pure substance, and remember that a pure substance is an element or a compound, that determines its identity. So it's the number of all of the atoms that you have there. So, you might have like 3 carbons with 2 hydrogens, whatever it might be, and also how those atoms are connected to one another, right? So you can think about this. If I'm connecting, say, X's and Y's, I could connect them in an alternating pattern like that, or I could connect them where we put all the Y's first and then we follow that up with all of the X's first, and then we follow that up with all of the Y's. And in John Dalton's mind, these are two different things, and that kind of makes sense, right? It's not just the number of each of the different types of particles, it's also how they're connected, right? What about, if we put them in a square? That would be interesting, right? Same number of each type of particle, but they're joined together in different ways, right? So that's kind of what John Dalton was getting to there. So it really is just following on from this kind of building block model that I was kind of mentioning before. Okay, then this is interesting, and it's really kind of quite logical now. He says a chemical change involves the combination, separation, and rearrangement of atoms. So a chemical change could be going from 3 X's joined together in a line to 3 individual X's. That would be an example of separation, wouldn't it? Right? That would be a chemical change, and these guys would be different substances after that chemical change because the atoms are organized in a different way. It could be, combination, where 4 of these X's come together to form 2 things that each have 2 X's, right? Could be something like that, yeah? Or it could be rearrangement, right? So we have X, Y, X, and then they rearrange, and so it goes Y, X, X, right? And so that's what's happening in a chemical process. The way that the atoms are connected to one another is being reorganized. Now, we're not losing or gaining any atoms. We're not changing one type of atom into another type of atom. We're just reorganizing how the atoms are connected to one another. So that kind of comes in with his 5th point. He says that atoms cannot be created, destroyed, or transformed in a chemical reaction. So we can't go like that, because that would mean that this X here got destroyed, right? We also can't do that, because that would mean that this Y here got turned into an X, right? And we also can't do something like that, because that means that, that's a Y in there, we've made an extra X out of nothing. We can't do that, right? Now, there are some limitations to Dalton's model, and we're going to see that when we learn a little about isotopes, but it's still really, really useful, and it's still central to our thinking in chemistry. So what do these things called atoms look like? Well, atoms have a diameter of around about 10 to the minus 10 meters, so 9 zeros. They count. One more. And a 1 at the end. Meters, so they're pretty darn small. And they weigh about 10 to the minus 23 grams. We can visualize atoms using a tool called a scanning tunneling microscope, where we drag a tip across the surface that just has one atom at the very end of it, and the tip is connected to one terminal on a battery, and then the other terminal of our battery is connected to our sample. And as we move across the surface, when there's a little bump on the surface because there's the atom there, we get more electricity flowing, and we can kind of do some electronic trickery, and we can get an image of an atom. And it's kind of interesting. The first people to do this, they worked at IBM, the computer company, and they used the microscope that they had invented to spell out, the world's smallest billboard in xenon atoms. And they actually went on to win the Nobel Prize for this work and for the invention of this microscope. So back in the day, the images used to be quite fuzzy, but now they're like really, really sharp. And this is the surface of silicon, which is what IBM were interested in, because what do? They make silicon wafers, right? Or silicon chips. So yeah, that's just kind of an overview of the first modern atomic theory, John Dalton's model of the atom and of chemical reactions. And we're going to expand on this, and we're going to present you with more modern quantum mechanical models of the atom as we kind of move through the class.